Good afternoon, everybody. Those here and those following us remotely on YouTube. I have the great pleasure to introduce to you a double session. The two speakers, two Miguel, but I think it's going to be a very interesting afternoon. So I will start by introducing our first speaker, Professor Miguel Fernández Ruiz. He's from Madrid, Spain, graduated from the University Politécnique of Madrid, where he obtained his PhD as well, with distinction, and then he started a career in industry as a consultant in a company, Design Office Pros and MC2. He also spent some time in Lausanne at École Polytechnique. So he combined a professional career and a research career, being currently full professor of the chair of structures at the University Politécnique of Madrid. So welcome, and thank you very much for your availability to talk to us today.
Thank you very much, Mr. Chairman. It's a true pleasure to be here with you, to find old friends and to meet new ones. So I will be introducing you to my lecture, which is named The Science and Engineer, what is a continuous evolution. And I think my intention will be to share a number of thoughts with you at the very beginning when I was speaking with Jorge Conde on what to speak, what to say. And we decided to speak a bit on the perspective that we're having on engineering. And so I will present this perspective very much based on my professional experience. So in my company, which is based in Switzerland, so you will see many projects which have this culture of Switzerland. And also I will show researches done at university, but basically now those that are occurring at Madrid. So all the work that you will see here, and this I want to credit everyone for this, it would have been impossible without the help, the support, and the ideas and the very hard work of many colleagues from the company, Duarte Faria, Antonio Garcia, lots of people also at the university, Leonardo, Hugo Corres, people from Lausanne, already Muttoni. So I will present this, but really consider this also on behalf of many colleagues. And so, starting with this line that we're saying, okay, how we evolve. So we need to put a starting point. And this, I set it arbitrarily in Rome. And why? Because perhaps it's the culture we have inherited. And when we revise what ancestors of our profession were doing, we see very, very interesting aspects. First one is that we acknowledge what is an aesthetics. Aesthetics is really what is remaining from an ethics and a technique. So all the Romans, they were very good in a technique, which was stone cutting and masonry, and also they were clearly having ethics, and ethics in saving materials and having efficient structures. And all these merge into these outstanding structures, which have been also lasting, and that show that our profession is not for the sake of doing it, it's really a necessity from society. So this profession evolved during centuries, and in many, it was kept also from what we call the master builders, as this is a cathedral I like very much. It's from Palma in Spain. It has the most slender pipes in Gothic cathedrals. And actually it's very interesting because if you go there, you will see that not all of them have the same slenderness. In fact, the first columns, they were more slender, and then they started buckling during construction. And so they corrected it. And this applied what was the characteristics of this period, which is named that engineering, if could be named that way, was governed by what we call the empirical method. Later on, there was a tremendous shift. It was in the middle of the 18th century, where there was the system of the conseils in France that were created. And there was really a very severe evolution in the profession. We were not longer governed by what was this empirical method, but what we could call at that moment already the scientific method. The scientific method is based on the observation, derivation of theories, and on that basis prediction of reality and acting. And also, at the same time, also some words started emerging as civil engineer, 1750, claimed by John Smeaton, the one of the concrete, and who started speaking of civil engineering. And I think we have to get to know, at least me, I need to know what civil engineering is, and I spent some time on that. And I found a very nice definition of what we are, what is to engineer. And to engineer, which is a verb in English, at least in Spanish we don't use it as a verb, but to engineer, well, we say when an object is engineered, it is planned and constructed using scientific methods. And I think here there are the two main components of engineering. So we are using scientific methods, we are using science, we are using knowledge, but we are doing more than science. We are constructing, we are planning and constructing. And this is what is these two souls that are living inside us. I always thought, are we scientists? I don't think we are pure scientists, because scientists is describing nature. So you could say where a planet will be in 10,000 million years, exactly at what position and which spin. So you describe nature in a most accurate manner you can. But an engineer is a bit different. We are acting on nature. We are transforming nature. So an engineer needs science, but can not only be based on science. It needs creativity. It needs a human step to transform. And this is, of course, takes lots of responsibility, and this is one of, citation of Joseph Conrad. There are many others of this sort, but that only those who do nothing make no mistakes. And this is something that we have to be aware of. When we are committing absolutely, surely mistakes. We do everyday mistakes. Me, for instance, I do mistakes. We have to do control and to see how it works. So I think this responsibility is a very important part of our profession. But also in this separation, in this split of the 18th century, there was also in the master builder, there was a component that was separated from our profession, and this is the one of the architects. And it has been curious because there is always debates on what are we. This is the very well-known drawing of Le Corbusier, a Swiss architect and then turned French, and where he's describing that we both are working in the same profession mostly, but the architect is more working in the sphere of the human, and the engineer is more working in the sphere of the techniques, of the knowledge. And this drawing to me has something very interesting, which means that architect and engineers, in some sense, they have to align. They have to share the same ethics. In fact, at least, if you want to have a good work done. So it's nothing that your architect wants to save a lot of money and you don't care of it, or the opposite, that you want to save money and your architect doesn't, or that you are very careful on what happens with environment and the other part. But once you find friends or colleagues, architects, that share your vision and you can align with them, then it becomes something which is very, very nice. And this is not only by chance, it's just in your profession, you will find people where you can align with. I think this is an interesting, very interesting picture. And how this evolved since then. So I think this is also very interesting to know that we saw that there was this aesthetics and in our profession, even after this separation came, we kept on having this sense. And I like very much also the sentence, nulla estetica sine etica. You can't have aesthetics without an ethics. And I think this is very well reflected in what we have done. This is, for instance, a very well-known work of Robert Maillard, Magazzini Generali Chiasso, in southern part of Switzerland, where you see this shape, which could be odd at the very beginning and say, well, perhaps it was just an architectural willingness, but actually not at all. In fact, it was a reflection of a clear ethics. As you know, when you want to save as much material as possible, then you are doing what is called a funicular shape. So everything is only tension, only compression. This would be one funicular shape. We could also have an arc with a tie inside. Every load is deviated. But they have a property, which Robert Maillard knows perfectly, that if you keep the distance between the tension and the compression cord constant, you can deform it This is just by changing the force. In this case, this compression will turn to be a tension, and then you can deform, but it is still funicular shape. So the shape that we see here is the result, again, of an ethics of the engineer, an ethics of the architect, saving material, and this reflects in this aesthetics, which was characteristic of these works done in the first part, at least of the 20th century. Also, well, Pierluigi Nervi, very good exponent, Italy in the autarky. Well, it was a complex period, but we see this ethics of saving materials, and has it become that way? Not necessarily. I think later it evolved in construction, at least in Switzerland, when I've been working more to what we have been calling the structural truth. The structural truth is what you're seeing with architecture, is what is resisting. No? So the walls and the slabs, which you see as a structure, it is the architecture, and the architecture is a structure. It's a very interesting movement. I've been working a lot on this movement, but with some distance, I would like to see or to discuss with you if we are going in the right direction, even if it is very appealing and intellectually very appealing. So this is the arrow of this short history that I wrote with this really clear cut in the middle of the 18th. And at a very different scale, very different, very much shorter. I wanted to show my time arrow also. So I really realized that now, when I came here in Madrid, if everything goes right, I will be in the middle, right in the middle of my professional career. So I started in 2001. I will end up in, if everything goes right, in 2047. So. I already did some works, and I have to say that I'm very proud of them, but I've been evolving. It's not that I'm critics to what I did, but at least I'm evolving, and I want to share this with you. I will start by selecting these works and trying to think what may come out for this remaining part. So let's start with first one, Muttoni. That's a foundation that was done by a person that wanted to host writers in the middle of the Swiss forest, in the Jura forest. This is the place, is Montréchet. It's a very beautiful place, and the idea of the architects was to develop this village like in a dialogue with the canopy, with the tree canopy that was there. So first ideas when we tried to discuss with the architect on how to do it was just getting again to what was done before. And there are many ideas that might be inspiring for canopies. This is, for instance, the Magazzini Gatti, but they are always based, they were based on the directions of what we call the moment tensor. A moment tensor is a 3-component tensor, so 2 bending moments and 1 torsion moment, so 2 principal directions, and this leads to these shapes where we are having the 2 principal bending moments. In this case, we thought that actually a tree is not behaving like this, and it is more related to what is the shear field. The shear field, it has 2 components. It's a vector field. It's not a tensor field. And this vector field, 2 components, Vx and Vy, can be characterized, obviously, by the principal direction of the shear force. And if we try to draw that, it's very interesting. What you get is something like this. It is the path that a load applied here will follow, if they are following, to go to the supports. It's giving you like an idea of how the structure is behaving. And also, even more interesting, it reacts to the way you are loading. So if you are loading in this type of symmetry, this load is going to the supports following this path. But if you're closer to the support, then this load will concentrate and everything will change. We found that inspiring, at least for getting to our canopy, and we started working with the architects on how could this be shaped. And then this gave these drawings, this shear field, and also that could be very well adapted. For instance, if we removed some of the columns that were there, we actually adapted to the canopy. So we were reacting to the decisions taken by the architect. And with all this, and discussing with them, we came to quite a strange shape. And this is a very inspiring moment when you come here, but later you have to build it. This is also the difference when you are a civil engineer and you are working on construction. You say, but how can I reinforce this? And this, I think, is something good that I learned in this project, is that when you are finding this as a challenge, you really need to go to research. And you don't have to be ashamed of doing research. You don't know everything. For instance, here we thought perhaps a good idea could be combining flexible wires inside fiber reinforced concrete, because this is helping us to reinforce all of these parts. So we try to characterize this behavior, which we haven't seen before, by testing different mixes of fiber reinforcement, how was also the bond, and eventually we tested beams to see that there were combinations without fibers that strength was not that much, and there were problems in reinforcing. When there were too much fibers, the response was stronger but much more brittle, and so that there was a good combination in between them that was working fine for us. Then we scaled that to prototypes, testing them and trying to learn how it worked. This was eventually how this canopy was built. So quite big one, 4,500 square meters, and it was aimed to suspend a number of huts. So that in order to build it, we built the scaffolding and all the plates, the formworks. These are the columns actually that were placed with a punching shear head and reinforcing, combining ordinary means and ties. And this is the way that the suspended huts were suspended to the canopy via these steel heads that were embedded in the concrete and helping to take the punching of the load. Also, there was an arrangement of a post-tensioning, as you see here, when we had the largest span. So we combined everything, but eventually it worked quite well. It was a very self-compacting concrete, despite also the presence of the fibers. It went nicely, and we could suspend. In the end, that was every one of these projects was a challenge. We suspended these huts where the writers, with the scholarships of the foundation, they could be hosted. So each one was with a different team of architects, Alejandro Aravena from Chile, MK27 Norway. So many different architects, many different sensitivities. It was a very interesting project. What we learned from this? I think one interesting lesson is that the sound conceptual design in a good dialogue with architects, they lead to very interesting solutions that are very inspiring and very sound. And also that we need to use to implement new materials, and we don't have to be scared of doing that, to improving the knowledge. And also I always encourage to do prototypes before going into the real scale. But, and this comes also with some time as self-critics, which I wrote as, where are the limits to structural exploration? Or this might be expensive, this is justified, but this can be summarized in a smaller sentence, which is it really justified to build what could be called as expensive toys for rich people? No? In the end, it's not all this an expensive toy for rich people. Is this justified? I think this is something we have to ask ourselves. So I enjoyed a lot this, but in the end, I'm not sure that it was the right means. Then I will move to another very interesting project that was a concrete shell in Chiasso. It's the southern part of Switzerland, the same actually where was the Magazzini Generali from Robert Maillard. That was a concrete shell that was built here. It's in the borderline with Italy, and it was a shopping mall. Actually, at that time, the euro was quite strong, and the Swiss franc was not that strong, and there was many people coming from Italy to do shopping. Then it came, it was the opposite, and so the shopping mall is no longer working well. It's almost closed. And why a concrete shell? Because the first project was timber, and it was very thick beams, done timber. It was working like frames, actually. And what we saw is that doing a shell, we could reduce severely the thickness of these elements, and even it seems that it might be not a big deal with this shape, it was a huge difference in terms of the usable area, and particularly those on top. So the project, when it was that way, it was economically not interesting. When the usable surface was higher, it was fully interesting. And so this is why it was just economic reasoning that guided through going to a concrete shell. It was 100 meters, almost 100 meters span, 50 meters span in the other direction, 27 meters high, and the ellipse, so 23 meters over the ground, and it was between 10 and 12 centimeters thick. So this gives an idea of the efficiency of this structure. So 10 centimeters thick, 100 meters span. So something also that I learned here, roughly, was that you need to identify what are your governing limit states, and these are not necessarily the ones that we are accustomed to. For instance, first one, I think we could be accustomed to is what happens with the membrane forces. So this is trying to crash, so it is dilating, and in the equator region, and you get massive traction tension forces. So what you need is to arrange post-tensioning here. Okay, but this I think we could all solve, but then you go to more exotic ultimate limit states. For instance, buckling, and buckling is the governing, actually, is the governing limit state for shells of this type, which are not very curved, and the thickness is small. So we needed to investigate multiple modes of buckling, local, and reducing if the flexural stiffness was higher, was lower, and so on. And also a third failure mode, which is we many times forget, at least I was not aware at the very beginning, which is what we call it's the boundaries, it's the link to the boundaries, it's what we call the silo effect. And there has been many failures in the past, because when you're having a silo like this one, due to the pressure inside, it is dilating, but the support is not dilating, so you're getting your wall, which is moving apart, and then you are getting an eccentricity, a huge eccentricity in a membrane. Same is happening here. So the whole ellipsoid is dilating, and then you get an incompatibility here at this point. This creates very large bending moments, and particularly large shear forces. And this depends also on the degree of clamping that you're having. Also, it's the same as in stress ribbons. So again, we needed to better understand this key issue, this key piece part here, and then we went to do some testing on real scale elements where we tried different arrangements of shear stats, concrete with fibers, reinforcement, until we found something that was very convincing, that we had sufficient deformation capacity to minimize these internal forces. Then again, before going into something so complicated, you need to do a prototype to understand what you are doing, to understand the mix that you are going to spray and to improve it. And once we were convinced, we started with the construction. And this is surely the least convincing part of what we did. This is the scaffolding. It was timber, and it is a whole structure which was useless thereafter. But a shell is very sensitive to imperfections, and it's very sensitive. 10 centimeters thickness shell, when you are deviating some centimeters, then you get severe reductions of strength. So this is the solution we found, but surely was not the good one. But at least it worked, because we could then do all the internal cladding, and then put the reinforcement, arranging the studs, arranging the post-tensioning, and then we went into the construction. This is the region where we were very scary on these movements that could have in the lower part. This is the region with pre-stressing, and the concrete was sprayed dry. It was dry way, sprayed in the bottom part, and on the top part it was just simply poured, where the slope was low. Also, something that I learned perhaps a bit late was that when you're doing a shell, you need to think, how are you going to decenter it? And the failures, the structural failures in shells, they are normally while decentering. For instance, the Loma de Cuernavaca of Candela, it was decentering, because if you have a very strong point, then your shell will punch at that region. So what we did was that we applied first 25% of the pre-stressing horizontal, then we decenter horizontally, and once it was decentered horizontally, then we applied the full pre-stressing, so we had all the pre-stressing inside our shell, and at that moment we started decentering just in the lowering the scaffolding of the top part. So it was very tricky. We really need to think this quickly because they were already trying to cut all the elements, and we say, okay, let's stop just 1 second, because if you are decentering everything and giving here strong points, then we will have a failure. So I think you need to think before starting. That was the finished work. It worked finally within the budget. It was not expensive, because as a facade, actually. And I think what we learned is that the shells, they are extremely efficient structures. Be careful with these limit states. They are not the same we're accustomed to. Keep on being encouraged to do prototyping, and as self-critics, you need to think different before phone working. We need to do something more. So now we move to the third project. That was the School of Ursi. And that came in a time where things have changed in Switzerland. I don't know if that's the case in Portugal, but things within these years they changed radically. There was people were starting to say, okay, you are destroying the world with concrete, you need to build with timber. And someone said that building with timber would save the world, building with concrete would destroy the world. Someone said that, and everybody, we thought, okay, perhaps that's right. So let's start building in timber. And I was also taken by this. And the positive thing is that I started working with timber, which is a very interesting material itself. So this project is in the French part of Switzerland. It's in Ursi, this small town, which has a forest. And that was interesting because the village was collecting local forests for 2 years. For 2 years they were collecting local forests, and when they stored it, they said, now we're going to build a school with that. And so they made a competition that was won by some architects, Rufier Shahab, and was a full school in timber construction. And we were working with the architects, giving shape to this school. And there I learned interesting things, that the language is a bit different. No? So you work with frames, linear elements, massive prefabrication of everything you are doing. And it also, you learn the very interesting property of lightness, something that you take with very limited means, construction means, and you can place, arrange, you can prefabricate, go very, very fast, and get the result really in a record time, something which I could not do normally with those means in concrete. And this is what comes out, which is very, when you see the photograph, I think it's very appealing. No? It's very nice and seems very warm, but to be completely transparent with you, it doesn't work. It doesn't work. It doesn't work, and it doesn't work in summer. And this is because in winter you're getting lots of heat, and that's good. But in summer, this is full timber, and if you get full timber, well, here we eventually put some composite because the topping of the slab was concrete. But if it is full timber, what happens is that you have no thermal inertia. So during the day, you're having the radiation, you're having the heat here, and all that heat is not stored anywhere. So it is very, very warm inside, very warm inside, very difficult even to work. While when you're having a concrete structure, then the concrete is taking care of this, is storing this heat, and then during the night you can open the windows, the heat will go outside, and then it's much more easy to work with. So even though it seems very nice, we have to be a bit critics on that, I think. In any case, you can build it quickly, and I like the next photo a lot because the children were very happy the first day, and I think the story went very well. But we have to be careful. Lightness is a great advantage, I think. But we need to use carefully timber. So timber is local timber, is a very good solution. But we don't have sufficient timber. Here you can build one school every 2 years, yeah? But you cannot build all of the houses that were going to be built. So otherwise, you start importing or getting timber from outside. In Switzerland, first was from Switzerland, later was from Germany, later they were speaking that it was coming from Finland. I heard that it was coming from Russia, no longer, since the war. But we claim that it is local, it is sustainable, but it is not sustainable because simply there is not sufficient timber. So I think if you manage to do it with local timber, this is very nice. Prefabrication is a very nice thing, but please pay attention, where does it come from? And also, please pay attention that the production of heat and the production of the energy consumption might be very different to what we are accustomed to. And also, we always say, no, it's very nice, but well, this might be a personal choice. Is it nicer than concrete or steel? Well, one might decide. So let's move to something which keeps on evolving, and this is more related now to research. And this is about the textile reinforced concrete. And textile reinforced concrete is a research we have been carrying together with architects, Patricia Guaita, Rafael Baur from EPFL, and also Sergio Eckermann from FAUFBA, Salvador de Bahia in Brazil. And we were working on the legacy of João Figueira Limas. Lele was a very incredible architect, Brazilian architect, that developed the concept of argamassa armada close to ferrocemento. And that concept was based on a very simple modular system, construction of full language construction system. And Lele is an incredible person, he's an incredible architect. Here you see with his friend Oscar Niemeyer. And I'm always surprised of this. When we are speaking of aesthetics, I think that you can see the change, what happened in the mind of Lele between 74, where he was really in brutalism, so Brazilian brutalism, to 88, Argamassa Armada, something extremely nice, extremely, really opposed to brutalism. So what happened in between these 14 years? How can someone give such a big step in 14 years? And by speaking with Sergio Eckermann, we saw that actually there were precursors. This is the civil engineering school actually in Brazil, Pavilion. It was told by Guilherme Melo. He already was taking in brutalism some of these elements, but particularly in '77 he worked in the upgrade plan of Salvador, where he discovered the necessity of light elements, self-construction, and working locally. And I think this inspired him a lot when he was changing to Argamassa Armada, to this system, modular system, by saying, okay, self-construction, so communities, they can do that. You can do it with limited means, you can do it with limited amounts of material, and it is towards what we call the social concrete. And this is a very interesting evolution of concrete, but we have to say that again, it has been partly failed. And it has been failed because this is ordinary reinforcement inside very thin elements. So they have massive amounts of corrosion. So these buildings, they are not in the same state now. So working as a research, we try to upgrade this Argamassa Armada by using textile concrete. And in textile concrete, we are replacing the steel bars with a textile made of carbon. Normally, what could also be aramid or other textiles, but normally it's carbon, which does not corrode. So you can have very low thicknesses and it will not corrode, but even better, as it doesn't corrode, you do not need to passivate anything, so you can lower the clinker. So you can use lower clinker cement mortars. And this is very favorable in terms of environmental impact of this material. Then it seems then it is perfect. What is not working? It is expensive, but not that expensive. What is not working? Well, that it is an extremely brittle material. So once you get to its strength, bam, simply fails. There's no utility, nothing you can do. And this is very scary. But again, working a bit and thinking on structures, you can do something. For instance, this is one of the beams designed by Lele. This is one of the original beams, EX beam, designed by Lele. These are this type of elements. And we saw that they were very favorable in these conditions, because even if you have brittle reinforcement, with this shape, you don't have sufficient compression region. And so when you test this type of structures, what you get is not that it is not failing due to tension, but you're failing due to compression, insufficient compression. And also, by playing with the diaphragms, you could also have different shapes which are governing, different waves that are governing, and you introduce some level of ductility in your structures. It's not a ductile behavior, but at least by using the concrete, the toughness of concrete in compression, you can do something. So I think that that's a good lesson. Don't think that you have to get rid of it. Perhaps you have to think on the structural response. This is the pavilion we eventually built. They are shells composed of column shells, and all you see here, even if they seem steel pieces, they are all textile reinforced concrete. The shells, they are 9 millimeters thick, and everything is light enough so that we can build it by ourselves. This is, by the way, built with students from Lausanne and also from Brazil that come to visit us every year, and then we are building together this pavilion, which is fully modular. We can assemble, disassemble, and trying to make a step forward. So what we learn again, lesson learned, lightness again is a very great advantage. We can lower clinker content, we can prefabricate, we need to work with architects, and also we have to be aware of that. We don't still understand how to use this material. But again, self-critics, no code provisions, we can't use that. What happens at design values, we need still more knowledge and to expand it to different contexts. So this fulfills a bit this arrow of time also of my experiences, and I think now what comes here? What may we thought that comes here? And just giving some thoughts on that. I think, and we are seeing, even if in my experience, that we are moving towards what we are calling sustainability. And we don't even, at least me, I didn't understand at the very beginning what does it mean. Because sustainability, it stands on 3 pillars. It's not environment. It's economic, social, and environmental. Something which can be environmentally very sustainable, but you can't pay that, it is not sustainable. And also, if it is extremely environmental and even very economic, but you have to import everything from, I don't know, from China or even from Spain, but you cannot develop your local industry, your local people, it is not sustainable for you. So you have to account in a broader scale, and also the multiple stages. So it is not only the construction, but there is the in-use stage that we're seeing for timber, end of life, beyond cycle, recycling, reassembling, and what can we do? So in this frame, what I wanted to say, and coming back to the Ursi case, to why we did this in timber, and why everything says that things in concrete doesn't work, we wanted to understand in terms of research now, that was done in Madrid with colleagues, how bad was concrete? How bad is concrete with respect to timber? I think this is a very pertinent question we have to ask ourselves. Are we banning concrete construction, saying it is the worst construction material, the worst thing can happen to the world? Okay, how much is it? Is it really so worse? It's so scary. So we compare what is a typical design. This is a flat slab, 4-story. Well, this is a typical Swiss design, by the way, with flat slabs. And then we say, okay, this is the flat slab, but this is not the only way we can build with concrete. So let's try again also some others, as a drop panel, for instance, a waffle slab also, which is old shapes. But here there is lots of material that we are not using, because here there is lots of material in positive that we are not using that you can remove, because you need here more for control of deflections and punching, but you can remove, save lots of material. Okay, let's try others. And also let's try what happens in timber, full timber, composite timber, concrete construction, and also, why not, steel, concrete, composite. So we said, okay, let's see how worse is concrete. And then the solution was quite surprising, because it is not that bad. It is not that it is not that bad. It depends on how we use it. In fact, it's a matter of structural efficiency. So, first of all, this is a plot which is saying, with respect to the span length, what is the kilograms of CO2 equivalent, so accounting for other greenhouse gases effects, per square meter of build. So we tried saying first, we started with a very dummy reinforced concrete flat slab. And you see that for long spans, it is not good. And I think it's correct. You are putting lots of material that are meaningless just to have a flat soffit. So this is not good for environment. This is even perhaps might be competitive, but it is not good. However, a first parameter that we have is that when we are doing with an architect a project, we might be reducing the span lengths, and then we are actively influencing in this amount of CO2. So via project, we can also be improving. But furthermore, if we are removing this material which is useless by means of drop panels or of waffle slab, what we see is that we get extremely efficient solutions, even more efficient than timber solutions. And this is because we are now using the material in an efficient manner. So you can combine even medium or large spans, but saving materials is sufficient. The concrete itself is a material which is polluting very low. This we have to know. The problem is that we are using too much of it. Also, the timber, it depends if it is a standalone, if it is composite, and also if it has connection pieces. If it has connection pieces, then it is much worse. And also the timber, we use normally glued laminated timber, and this is something that you cannot even burn due to the gases that it is detaching. So it's something which is an artificial product, even if we claim it to be natural product. And we see that it can be as good as concrete solutions, as bad as concrete solutions. Same happens also for steel concrete composite. And this that we found for this case, for this really academic case, we found also in projects. This is a design competition we won in the village of Morges in Switzerland. It's the roof of a sport hall, and we won it with a concrete, pre-stressed concrete solution. And the client, public client, said, no, let's do it also in timber. We want this in timber because we want a sustainable solution. And we say, oh, okay, and also let's try what happens in composite steel concrete. So we tested what came out, and just to come to the end. In the end, it was the client that decided. It costed more. And in terms of sustainability, here we are comparing again the kilograms of CO2 equivalent per square meter for the three solutions. And what you see is that, again, it depends how you're building, you're getting good or bad solutions. For instance, if you're using low clinker content cements, CEM2 or CEM3, this is comparable, fully comparable to an already optimized timber solution. When the glued laminated timber, it depends whether it is local. Of course, if it is a local source, you are polluting very low, but if it is imported timber, it is not that good. Same happens again also for the solution with structural steel. Well, all Europe will be more or less here with the recycled steel, even more than 85% of recycled steel. This will apply only to countries where they do not have, or they are not using recycled steel, as China. Chinese is starting now to use it, but this can be very, very bad. But normally we could be building in a comparable manner also with steel. And this that we have seen for a building case-based study, also for a building real project, it also happens for bridges. This is a true bridge. It was a project of École. And this is a bit different because foundations, they have a huge impact here. So the lightness of the structure might have a huge impact. Also piles. And by comparing different solutions, again, in terms of CO2 equivalent per square meter, we saw that it was in situ conventional or precast beams, ultra high performance fiber reinforced concrete, or even a composite one. Depending on the efficiency of our solution and on the selection of our materials, this is because in Spain it is not allowed to use century for pre-stressing. But if you could, why not? all of them you could find efficient solutions everywhere that are working perfectly. And also you can find very poor solutions depending on the selection of materials that you're using. So what we learned from this, before Jorge kills me because I'm getting overtime, so sustainability is a sensitivity and an ethics is not a calculation. It's not something you may calculate and say, I've done it. Materiality, the material that we're using is not defining sustainability, but it is defining the structural efficiency. So you have to combine a good selection for your material of the structure, so a structural efficient material, with a good selection of materials that are reasonable with a low environmental footprint. And this is something also that we have failed as engineers, at least in Switzerland, completely to communicate to owners, completely failure. And we need to make a bigger effort to communicate to students and to owners so that they are not led into wrong directions. So that was my last slide, and I wanted just to say that I was influenced by many people, engineers, much more clever before me. I'm contributing in this way. I don't know what will come here, but that I will be more than glad if in 2047 some of you, Miguel Ferreira, you invite me again to come to Coimbra, and then we can discuss again what happens, how was all this field, and what may come out for the following generations. Okay, so that was everything. Thank you very much. And
thank you very much. We'll save the questions for the end of the two presentations. So we proceed immediately with our second speaker, Professor. It's a pleasure to welcome Professor Miguel Gómez Navarro, who's a structural engineer also from Technical University in Madrid, a PhD from Switzerland, from Lausanne. So a common point here of having spent some time in Switzerland, in Lausanne, and then he combined academic and professional activity with a lot of research and work on with his PhD thesis on concrete cracking and deck slabs of steel concrete composite bridges, and then work in Julio Martinez Calzón MC2 studio, where he developed a lot of very interesting projects. I'm sure we'll hear about them as well. And then more recently, he spent some time as Dean and Director Provost of the European University in Madrid. And now more recently, he's in charge of the BIS Structures Design Office in Madrid, combining his activity with being a professor at the universities of Segovia, Madrid, and the Technical University of Madrid. So you have the floor. Thank you very much.
Thank you very much, Professor Simoes. Thank you very much for this welcome, and I have to congratulate Professor Simoes and Professor Jorge Conde for organizing this cycle of lectures. That I'm a little bit ashamed of being part of it, because all the people that has been here before me, they are great designers, great researchers. That is the case of, oh, it's finished already. Good. Thank you. I've been quick. No problem. Just a joke. No, I mean, it's been a great effort, but I hope you have enjoyed of the company of my colleagues from Spain, that I know them quite well. Some of them, they are good friends and companions. Miguel, he didn't include me in his references, but he started working with me. So all that he knows comes from me. Of course, that's a joke, because you can see that we can have hope in the future of humankind, because he's younger than me, he started working with me, and you will see that his lecture is going to be much better than mine, and his activity is much better than mine. So I'm a little bit with pressure being the last one in this cycle. I hope I can keep the expectation a little bit as the others offered. I have used this title for the conference because I love working with architects. I started working too just as a bridge designer, but I spent a lot of time working with architects, because my master, my real teacher was Julio Martinez Calzón, that was one of the best structural engineers in Spain, the one that presented in Spain or introduced in Spain composite design. He was very good, he's very good. He's not active any longer, but he's a very good structural designer. And he helped me to understand the relation between engineers and architects designing good buildings. So I've learned a lot from him. And then, as Professor Simoes presented, I worked as a dean in a school of architecture. That is quite tricky. Being a civil engineer, work as a dean in a school of architecture is not simple, but I learned a lot from them, and I think that when we work together and we understand each other, the different points of view, we do better buildings, better structures, better things for life. That's why I want to compare things from the different points of view. And as I used to say to the students, you don't have good or bad structures, you don't have the right solution. You have the right solution for a different points of view. We as engineers, we are very focused on finding the right solution. I used to say when I was at university that we as engineers, we look for the only solution of a problem that has very clear boundary conditions, very clear data, and it has just one solution, and is the solution that you have to find when you are a student at university. But real life, real projects, you don't have clear boundary conditions, you have no clear data, and of course there is no one solution. You have to be able to put together a lot of different things, and then it will be a good solution. We never know if it will be the best or not the best, no? And I wanted to present some comparison of buildings that maybe they can enlighten this reflection. I wanted to start with some key ideas that I will develop. Complex buildings, they require thorough structural understanding. I think that more and more we have, I don't want to talk like an old person, but it's true that more and more this modeling thing makes us to forget that we need to understand what we are doing. Doing a model gives us good results, can give us a safe result, but maybe it's not a good solution because we understand nothing of what we are doing. And it's important when we prepare the future engineers and the future architects to make them understand the structural behavior, because if not, the buildings, they will not fall, but we will understand nothing of how they are behaving and what they are working, and we will find not good solutions. The good things of buildings that is different to what happened when we are dealing with bridges is that there is a lot of hidden resources available to solve the structural challenges. We will see now a couple of examples of the interaction between the different parts of the structure. That is a classical thing of buildings, completely different to what happens in a bridge. That is just a beam, very complex beam with big loads, but just a beam, or a beam in an arc or something like that. But buildings are an interaction of a lot of different systems, and we have a lot of resources that if we are clever enough, we can use them to make better buildings. Because there is a strong interaction between all the different structural systems that participate in that global system. But the backside of this thing is that sometimes we can have unforeseen situations. Of course, this interaction, if we don't control it, we can have some problems that appear at the very end, when we have already done the whole thing, and suddenly a problem appears because there is this interaction that sometimes can be good and sometimes can be bad. And this is the same thing as parasite effects. No? They are all connected, these unforeseen situations that sometimes they can provoke parasite effects. And I will present a couple of footbridges, because footbridges are nowhere, are no man's land, are in between architecture and engineering, and sometimes, at least to say this, that they need careful detailing, because the structures are a step much more complex than in buildings, and the detailing is very important if we do this kind of what I've called architectural footbridges, that are not normal footbridges. I'm not going to present Valladolid, that you know well, that you worked a lot, but that could be very interesting to be presented, because we work together in that footbridge too. And I want to start with this, that of course is not my design. I was going to change the subject of the conference, and I was going to call it useless structures. And tell me, it's not because this building is a useless structure, but I was very, very sad this summer because I went to Slovenia by car, and on the way back I decided to stop in Turin. And when I was in Turin, I said, okay, I think there was something from Nervi here in Turin. and I looked in internet, Palazzo del Lavoro, and I had this picture in my mind and these big columns that they have something to do with one of the buildings that we are going to see later. And I looked in internet, where was it? And I started to see something weird in the opinions in internet about the building. So I was quite surprised. And I was looking for this too. That is a very interesting slab like the ones that Miguel was showing before. And when I arrived there, I didn't see these, but what I saw was this. An abandoned building, completely abandoned and completely closed. This building suffered a fire that it seems that it was provoked from some real estate developers, all the class of people that want this building to be demolished. So now this jewel of the structural design of the 20th century is completely abandoned. There's nothing to do, and you feel that they are waiting it to fall apart by itself and to do something there like a new tower, like the one that Renzo Piano did 20 minutes ago, that you will see now in another picture. I think we have a responsibility to protect our patrimony, the things that we have built. And it's a pity that I think the buildings built in the 50s and the 60s, nobody understands that they are part of the things that we have to protect. We protect old buildings from the 19th century, from the 18th century, but these buildings, that they are jewels and they are very good buildings, we are going to have more and more problems because we need some money to be put inside into these buildings to recover them, to make them comply with the new legal issues, and nobody's going to pay the money for that. And we have the same problem with this building, that it was the first building I wanted to see in Turin, the Lingotto factory. And the Lingotto factory that is in all the books that we have read during our studies related to architecture. Now it's something without personality. They have built a so-called ecological garden on the top of the building. They have built this tower that is by Renzo Piano, that instead of protecting this building has decided to build a tower without personality there in the middle of Turin, and do this, I will say, not very nice thing in the middle of a classical masterpiece of the 20th century in terms of architectural and structural design. So maybe sometimes our structures are not so useful as we'd like them to be, at least for the society. And after this introduction, that it wanted to be a little bit provocative because it was so sad during this visit that I wanted to tell somebody my feelings after that. I wanted to look for an audience for that. I'm going to present some buildings, and we were very lucky at the beginning of this century. So these buildings are in a certain way a little bit old, because in the company with Julio Martinez Calzón, we were able to work on 2 of 4 of these buildings that were built in Madrid. Maybe you know the story that these towers were in the old sports fields of the Real Madrid, and Florentino Pérez was able to get the permission to transform the sports fields in these 4 towers and get a lot of money. So these towers are called Ronaldo, Figo, and I don't know, all the football players. But in Madrid they say that, no? They gave the names of the football players to the towers, because with the money they got from the sports field, they could pay all the football players. So we were able to work on these 2 towers, and I think that's an extraordinary opportunity in your professional life to be able to work on 2 similar projects in the same piece of land, same height, but very different situations, different architects, different uses, and that's why it's interesting for me to compare them, no? Because I was so lucky to work in these projects that I think it's interesting to explain this. So some ideas of the 2 buildings. Torre Espacio, that I would write TIC because that was the name that they used. It's 223 meters high, 78,000 square meters. Architect from New York, that they have done lots of towers, so they know how to do the thing. They have a broad experience for that, so it was very easy going for them. The shape is variable because it starts in a square and it finishes in this oval shape, and that influences a lot the behavior. And with this change of shape, what we do is we remove some columns. You will see now in some diagrams. So up here we have this ring of columns, and the columns in the facade, they disappear little by little, gradually. Torre Satir Vallehermoso, it was on a certain way completely different. Same height, 236 or 10 meters more, but quite similar. The complicated things in terms of architecture was that they had to combine a hotel in the 2/3, in the bottom 2/3 of the building, and offices on the 1/3, on the top third. The architects, it was their first, and I have to say, their only tower they have done. Rubio and Alvarez Sala, a very good team of architects in Madrid that I like them a lot. But it was the first time they did such a big tower, and they deal with a big challenge that is to combine hotel and offices, and that's why you see here all the rooms, and here an open space. Here you have all the elevators. You need a bigger number of elevators to combine hotel and office. That's a challenge too, if you compare that to the other building. And all the distribution and the exit stairs are completely different than to a normal building with just offices. And it's a constant floor shape, so it's like a cylinder with the same shape along the whole height of the building. This building, we'll start with the characteristics of Torre Espacio. This was a concrete building with flat slabs, 280 millimeters thick in the normal floors, with concrete columns and cores, high-strength concrete, C70, and as you see, the red columns inside, they run along the whole height of the building, and the green columns, they disappear little by little when the floor reduces the size. And we have a big central core that runs along the whole height of the building, and these two secondary cores, they disappear gradually when the elevators that serve the different parts of the building, they are not useful anymore. So we have, on the top, we have just this core. If we compare this to the structure of Torre Satir Vallehermoso, this is completely different in the sense that we have this huge central core, much bigger than the other one, because we have more elevators that they run along the whole height of the building. And this is a steel structure, or a composite structure, with three composite columns. We will see some pictures now, with one ring outside, another ring of concrete of columns, because this is the corridor of the hotel, and these are all the rooms. And this distribution, of course, rules how the distribution of columns and beams is going to be. And then we have this main ring of composite beams and the joist in the radial direction. So this is a composite structure and a concrete structure, so we can compare and to see who's better or worse. But it's a classical question, which of the two towers was more expensive than the other. And I'm not going to be so critical as to steel structures as Miguel, because being in a steel structure department is not very nice, Miguel. I think that you have to adapt your speech depending on your audience. Sorry about the bad joke. But in any case, we have just this core and the comparison. Of course, in towers, we deal with wind forces. And as I've told you, we were in the same space, same height. So we had to compare the behavior, and we did this boundary layer wind tunnel test in Canada. And as you can imagine, the forces are quite similar. These are the forces and moments in the two towers. So you see the forces are quite similar. The only difference is that Torre Espacio, as it has this funny shape with gradual variation, it has some torsional effects that are 4 times the ones that appear in the tower that is just a cylinder. But on a general basis, we can say that the forces are similar, so we can still comparing the two towers on the same basis. No? These tests were very interesting, and we learned a lot from this test in Canada. The difference, let's talk about the wind structure. How do we deal with the wind in the two towers? In Torre Espacio, we have the cores, and we decided to place an outrigger at 2/3, that is the optimal position of the outrigger. And then we found these things that you found when you are doing the models, and you didn't realize at the beginning, that the fact of having such a big number of reinforced concrete slabs, that they are thick because they are flat slabs, they create like a solid connection between the facade supports and the central core. And the distribution of the wind response was 50% the core, 20% the outrigger, and 30% the solid slab. So it's a big contribution that you have there for nothing, because the slabs are going to be there, so you save a lot of money for the cores and for the outrigger. So we have a classical structure with combination of core and outrigger. The outrigger is in the best position you can imagine, 2/3, the most effective one. The problem was to build this thing, this outrigger. It's located very high in the tower, 2/3, 150 meters, and we needed to do it with high-strength concrete, C70. And you can see here the shape. We had these walls, these radial walls and these facade walls to connect the supports with the central core. So this structure was fully in load. A lot of loads were applied to this structure. So we need to place a lot of cables here, and we need to pump high-strength concrete to a big height. And that was a big problem, because that's not a normal thing. You use high-strength concrete for columns that are at the lower floors. Here we had to pump high-strength concrete to a very big height, and nobody knew how to do that. So that was a problem, and the construction had to be in a certain way interrupted to do this complicated piece. Normally they were able to do one floor every 10 days, and they had to stop that cycle for 3 months to build this complicated element. We had these kind of problems that we like as structural engineers when we have to work with MEP engineers, because at the beginning nothing was going to happen here in the technical floor where this thing is, but then they decided, of course, that they needed to do holes for tubes in the place that we want them to be, of course. If you need to transfer the load from here to there, where do you do the holes? Here and here. I was lucky because at that moment Miguel was working with me. Then he decided to flee to Switzerland to earn more money than in Spain, and he was able to do these funny calculations with the stress fields and to find what we had to do to be able to resist with all those holes, placing pre-stressing, a lot of reinforcement, as you see there in what is written. It's quite thick walls with a lot of reinforcement and with pre-stressing. But I was happy because I had him and he did a very good job. But this was complicated to be built in any case. That's what I wanted to say, that piece was very good but complicated to build. On the other hand, in Torre Espacio, as you've seen, we had a big central core. Quite a big central core because we had a lot of elevators. So we were able to do just a central core for all the loads. We didn't have the slabs because the slabs were steel and composite, so they are not rigidly connected to the central core. So we decided to place an outrigger at the very top because we needed just a 10% more resistance compared to what is provided by the core. And just with that, we were able to satisfy the deflection limits and the resistance of the whole structure. So even if this is not the optimal position, with this it was easier to build, because if it's at the very top, you don't need to interrupt the construction of all the floors, and you can place it on the very top. Here you see how the outrigger was. The geometry here wasn't easy. We will come back to that. But the thing is that we were able to connect only these two supports here, because as you see with the geometry, you cannot imagine how to place easily the walls to connect the core to the columns to create this effect of outrigger. So it's only 6 supports, but the forces were not so big. We could make it with concrete normal, with normal concrete, C30, and the slabs were just reinforced concrete slabs without pre-stressing. So this was much more simple, even though the position wasn't the optimal, but the construction was quite simple. If you see here, the result is the same in the sense that the acceleration at the top of the tower is quite similar, 20, 21, the limit is 25, so we were fine. Here you can see that the rotation in Torre Espacio is much bigger. The two of them, they are under the limit, but the rotation in Torre Espacio is much bigger because of this torsional force that I have told you. And I learned, I had no idea, and maybe you know it either, that this rotation is much more important in terms of psychological reaction than the movement. Because if you are in a tower and you have another tower there and you rotate like this, you notice that much more than if you move backwards and forward. So this limit was much more relevant than this acceleration. And in addition, we were in a hotel, so all the movement problems are more tricky in a hotel than in an office. Okay, but the two towers, they have the same behavior. So having done this, we could compare them properly. Just a few words about the cost. You see that the reinforcement, the concrete in Torre Espacio, the concrete in Sacyr, the reinforcement in one and the other, and we made a figure of the cost, and you see that the cost in Sacyr are double the cost in Torre Espacio. Double, and we didn't do these numbers while we were doing the project, we did it at the end. And that's interesting to understand why these figures appeared, and this is the point of this part of the lecture. Coming back to the columns in Torre Espacio are reinforced concrete columns, quite big, because the lower ones, they have high strength concrete and 2 rings of reinforcement. The ones at the lobby, they wanted them to be thinner, so we put some steel profiles inside, and these are the columns at the top of the building. The columns in Torre Sacyr, they are composite because we use the steel profile in the center as a provisional support to create the steel structure. And then we pour the concrete around the steel element. Once we have used the steel element to place all the steel beams and joists. So this was very efficient. If we compare the columns, we have this same surprise of different costs, because you see that the columns in Torre Sacyr, they cost double, not double, but almost double than the columns in Torre Espacio. And we were either the same silly people in one tower or the same clever people in the other, but these were much more expensive. And this is the solution. This is the thing. This is the thing. This table is the thing. If you compare the distribution of the vertical loads, the distribution of the vertical loads in the two buildings shows you that in Torre Espacio, 52% of the vertical load goes to the cores, and then the other 50% is distributed between the main columns and the outside columns. But so you have a lot of vertical load in the central core. On the contrary, in Sacyr you have only 31%, and we will see now why. Maybe you already know why, but I will go back to the floor plane. So then you have more load on the columns than you have in Torre Espacio. That happens because, as you see here in this drawing, this is void. This is a vertical shaft for equipment. This is a vertical shaft, and this is a vertical shaft. So there is no connection. There is a very vague connection between the floors and the central core. That's why the vertical loads, they don't go to the central core. If you compare that to Torre Espacio, in this picture you can see it better. There is a very good connection between the floors and the central core. So the central core receives a lot of vertical load. And if I go back to this table, as everybody knows, in an element with bending moments, the compressive forces are positive. They help to resist the bending moments. So the central core, the cores in Torre Espacio, they are cheaper than the cores in Torre Sacyr because they have the positive effect of the vertical loads. That's why these figures are, these values are smaller in Torre Espacio than in Sacyr, because the core in Torre Espacio is better prepared for this combination of vertical loads and bending moments. And the core in Sacyr has only a lot of bending moment. It's huge, but it's not well prepared because it doesn't have vertical forces. And the problem is that, as the vertical forces, they have to be resisted by the columns, we need more money for the columns in the second tower than in the first. So you see, who's better or who's worse? It's no good or bad. The thing is that if you have to do such a complicated building to combine hotel and tower, it's not so easy to do a structure that is efficient. It's easier to do a simple building with just offices than this building with this combination of the two things. The slabs, they were different too, in the sense that this is a flat slab and this is a composite slab. This was quick to build, but not so quick as this one. In this tower, they were able to build one floor per week as a clockwork, because it was the same floor everywhere with the same distribution, so they did it very, very quickly. And this one, they did 3 floors a month, so it's slightly slower. But there's not a big deal in a certain way. The costs that you cannot believe really this cost, in the sense that you can calculate the amount, but the prices, the construction company will never tell you the truth. So these are official prices, and you see that, as everybody knows, steel structures are slightly more expensive than concrete structures. But there is not a huge difference. Here is not a big deal between the two towers. No? So, any case, as Miguel said very clearly and very cleverly, we design, but we build. So it's important to understand the consequences of our choices. And you see these slabs, the slabs in this tower were built quicker than those of Torre Espacio, 6 versus 9 days. And that is important when you do a tower. You need to go quickly and to have a cycle that is clear. But the columns in Torre Sacir were a little bit more complex than the cores and tower and columns in Torre Espacio, but that wasn't a deal. I think the procedure was clever and simple enough. And this was the big deal. The outrigger, the well-designed and efficient outrigger at Torre Espacio was a disaster in a certain way. Was a disaster because, as you can imagine, these towers, you start building the structures, and then they come with the facade after you, and then with the MEP, and then with the furniture. It was really funny because one day we were at the floor number 50 or something like that, and there was a failure, a problem in the elevator, so we had to go down through the staircase. And it was very funny because you could see all the stages of a construction site. At the very top floor, we were with the formwork. The other one, they were pouring the concrete. Then we saw the facade. Then we saw the MEP. And the construction offices, they were already on the first floor inside. They have demolished these provisional houses that they have in the office, on the construction sites. They were already in the tower. So you could see the whole process of construction. And this cycle, that is quite clear that they ran one after the other, was interrupted by the outrigger construction. And I still remember the phone calls of the owners telling me, what's happening with this outrigger? The people of the facade is going to catch you up. So please finish that, no? Because that was a very long time. And on the other way, the outrigger on the top of Torre Sacir, no problem at all, because that was the very end of the structure, and they were already doing a lot of things on the lower floor. So it wasn't so efficient in terms of structural design, but it was no problem at all in terms of construction complexity. So these two towers, it's important to understand that both the structures were well designed, because they responded to an architectural problem. An architectural situation that it's well designed too. So we don't have good or bad, we have solutions adopted to what we needed. It is true that the large shafts reduces the compression forces on the core of Torre Sacir, increases the force on the columns, and that's why this tower is more expensive in terms of costs of material than the other one. But at the end, taking into account the outriggers and the construction sequence, we don't know how is the real cost of the two towers compared. Because if you take into account this speediness of one tower and the other, one thing maybe helps to counterbalance the other one. But I think it's a good exercise to see how some ideas that you cannot imagine, they have such a strong influence in a building of this shape. When we started the two towers, we couldn't imagine that this effect of the bad connection between the slabs and the core would have such a strong influence on the design. And of course, when we build something at least 200 meters high, everything participates in the decisions. You cannot play with your normal ideas. You have to think about other issues. After these two buildings, I want to talk about another tower. That this could be really be called useless structure too, because this tower was done for the international exhibition in Zaragoza in 2008. And of course, they said that as this exhibition was ecological, sustainable, whatever and ever, this building was never going to be abandoned, and they were going to reuse the building just the very day after the international exhibition. If you go now to Zaragoza, that is between Madrid and Barcelona, you find a lot of abandoned buildings. Maybe you have seen the bridge by Zaha Hadid, the big a building bridge over the Ebro River that is completely abandoned. That costed a fortune, and it was a big complication to be built, and it's abandoned. This building that was supposed to be transformed in a hotel is abandoned. Nobody wants to pay the money for that. Of course, after the exhibition, a big crisis arrived. Some people say that in Spain we had the exhibition in Seville in '92 and the crisis in the '93, and the exhibition in Zaragoza in 2008 and the crisis in 2009. So maybe we should have done another exhibition last year to follow the rhythm of the crisis. But in any case, they said that this building was going to be not useless, and we have the same problem than El Palazzo del Lavoro. I'm not Pierluigi Nervi, but I helped to build useless structures as he did with his Palazzo del Lavoro. The architect was Enrique de Teresa, an architect from Madrid. The tower is not so big, it's only 80 meters. It has this funny shape because it's the drop of water. The subject of the exhibition was the water. It was the water exhibition, that's why it has this shape. And of course, there is a strong interaction between architectural and the structural design because of the shape and the complexity. I used to say that doing an empty building is more complex than a normal building, because the thing is that this building inside is almost void, empty, because they wanted, you will see a picture at the end, they wanted to place inside a huge structure that simulates a drop of water, a splashing drop of water, and it was suspended here in this inner void space that is something like 40 meters high. So we had to do an empty building. That being empty 80 meters high is not so easy, because you have to retain the walls and make everything to collaborate. So the building has a plinth made of concrete and a tower made of steel, with this empty space and with some platforms in this lower part and at the top part. And this inner space was supposed to host a hotel after the exhibition. That's why we had to design all the structures here to be able to suspend the hotel inside. That was the idea, no? You see the building from the air, and you see the water drop, and this is the concrete plinth. So the tower has to be supported by that concrete plinth that, as you can see here, it has a column distribution that is not related to the shape of the water drop. The column distribution follows this hexagonal or triangular shape, and the water drop has this other funny shape. So we had a big forces, big efforts to transfer the force from this beam, that is the beam that you see here, to the columns that are the line intersection in the triangles there. So the transfer of forces between the tower to the structure underneath were complicated. I put the picture of the Palazzo del Lavoro because the architect wanted us to use the same columns than the Palazzo del Lavoro. Maybe you remember that those columns in the Palazzo del Lavoro are hexagonal and at the lower part and a triangle on the top part. And he wanted us to do that. And I remember doing the drawings. You remember Alvaro, our friend, he was doing those drawings too, and we were insisting him, it's impossible, it's impossible, it's impossible, because the columns in the Palazzo del Lavoro, they are 40 meters high, and they are 2 meters thick. So you can do this funny shape of hexagon changing into triangle to the top with twisting planes. Here, it was impossible to do that in a 8 meters height. And that's why finally, when the construction company arrived, they say, if you want the building to be done in the time you have, the first thing you have to do is to change the columns. And we did this simple cylindrical, not cylindrical because they are cone, a little bit funny, but not so interesting as they were. So this is a transfer slab to transfer the load from the tower to the columns. And here you see the structural system. We have a facade, steel facade, that you will see now in the pictures. You have these two central cores in concrete, and these areas in clear gray are the slabs that we have at every floor. And then we have some ramps, helicoidal ramps, that run along the whole height of the building, as in the Guggenheim in New York, or all these kind of buildings that you know. But we have a very small surface to connect the facade and the cores. And the question is, how are you going to stabilize the facade? Because it's not, it's very big, a lot of wind, a lot of height, so we have to analyze clearly, and as you can see, we use the ramps to stabilize our facade. Overtime already? Hasta el cuarto, okay. I will finish. I will skip things. So, you see these central cores, you see the facade, and you can imagine that if you have just these floors every 3 meters, you cannot brace the facade that is quite tall. So we decided to use these beams of the ramps that are connected to the slabs that are connected to the cores to brace the facade. So these things of the structural resources that you can use if you think cleverly and you understand the concepts of what's happening in the building. If you don't think about the useness, the utility of this ramp, you cannot, maybe you have to do this facade stronger to be able to resist without buckling problems, because we have to reduce the buckling length of these columns. Here you see the ramps that are quite simple, still a structure with a composite deck. And here you see all the ramps that with this system we were able to calculate them just with the buckling length of the distance between the ramps. Here it was a problem because it was double the height, and it was in the worst part, of course, because that was at the lower part of the tower, because this ramp had had a different development, and we had no bracing situation. Here you see this is not so relevant. It's the connection between the slabs and the ramps, because they have to be suspended. The slab has to be suspended from the ramp in a point. The fireproofing and the global analysis that was required to prove this thing of the bracing effect of the ramps in terms of the global structure. But if you don't understand what you are doing, this global analysis, it's useless, because you don't know what you are doing. These are the trusses that were placed on top and on the lower platform for the structure after the exhibition. This is not so interesting in terms of interaction, just to show you the elements. And this is the void inside from below. This is from the floor, from the lower floor, and you see all the floors in between, and this is the shape. And this was the top platform where the restaurant of the tower during the exhibition was placed. Just to show you the funny things that you have to do in these kind of buildings, this was a structure that we need to place inside the escalators, because they wanted to do an escalator that is not supported on the landing. It's two stretches of escalator, so we needed to do this structure to place the escalator inside. So it was complex and expensive. We did this big one and these smaller ones, but as the building is empty, you have no point to support even your escalators. So that was a complicated structure too. And let me use 5 minutes, please, Jorge, just 5 minutes. I will skip the other one, but it's just 5 minutes. This, I still remember when Dominique Perrault, maybe you know him, this architect from Paris, he came to the office. He had 2 projects to ask us for our offer. And one was a huge building, a huge library, that finally it was Alejandro Bernabeu who did it. And I think they did a lot of money because it was a huge building, quite complex, but not so complex. And he gave us to do a footbridge. That the only idea that we had about the footbridge was this. He showed us on the piece of paper. He said, "Can you do this footbridge?" Okay. So instead of making a good price for the big building, I made a good price for the footbridge. Alejandro got the big building, and we got the footbridge, and we lost a lot of money. But it was interesting too. So he came with this. Dominique Perrault said, "I want to do this," and the thing is, the result was this. Maybe you have seen it on television, because now it's one of the more photographed spots in Madrid. All the tourists, a lot of tourists, when they go to Madrid, they took a picture here. you can see in the commercials, in a lot of commercials. I was looking for one of them to show it to you, but I didn't find it, but you can see in commercials. And it seems that there's a new film that it's on Netflix by a Spanish movie director that happens here too. Somebody told me the other day. So maybe if you see the film is called, I don't know, I don't remember. It will come because I don't remember the name. So the spans are big, 117 and 96. Let's say we are not talking about a silly footbridge somewhere in the middle of an abandoned space. It's big, and you don't see it here, but you see the dimensions. This is huge. This is like 10 meters in diameter, so it's a huge element. No? So you see this, and then you say, okay, this is easy. It's just a truss, no? It's just a truss. Let's go for it. I mean, it's a truss with a big static height, no problem at all, no? We can do this. We'll get money from this project. You say, oh no. And in this case, it happens as sometimes you don't think beforehand. You do your models, and you say, what's the problem with this? This is not a truss. Because what is the good thing of trusses? As everybody knows in this room, just compressive forces or tensile forces. But what happens if you take a truss and instead of having plans, you make them curved? Of course, this bar has a compressive force here and a compressive force here, but then it has a huge bending moment. So it's not a truss any longer. It has nothing to do with a truss, just the funny shape, but not a truss. And then you are in the middle of a big problem because you have to solve the structure that is going to be much more expensive and much more complex to analyze, not only because of the thickness of the plates, that of course they are big plates, but the connections there. Because here you have big bending moments that in certain cases you have to transfer them from one side to the other of the connection. And you have 6 bars here that of course these are not pin joints as you have in a normal truss. These sometimes you need them to be rigid joints, and it's not so easy. So detailing in an architectural footbridge, it's a little bit tricky. This is the result, ill-conditioned truss, as you can imagine. Sometimes we used to say, and we did a simple analysis, if this plate, instead of being this kind of fabric, steel fabric, that Dominique Perrault uses a lot, was a plate, a thin plate, but a plate, this bridge would have been completely different, because with this conical plate shape, the plate twisted around the axis would behave very well. But we couldn't count on that because this is flexible, absolutely flexible. So you have just your ill-conditioned truss to resist the forces. See the picture of the joint with full continuity. I recovered this drawing that is from 15 years ago, and I couldn't understand it. I couldn't imagine how we did this. And I don't understand how they were able to build this. I mean, the other day I was there looking at this plate and this, how were we to do this? Miguel wasn't there, so even after Miguel, we were able to do interesting things in our office. It's just to make you feel humble. And you see here the connection, the big plates, and this complexity. So the supports, I'm not going to go into that, because they were these small supports where you have to connect your truss with those small supports without any proper pieces, because the architect, of course, didn't want any proper pieces of connection like rubber bears or things like that. Everything has to be hidden. You can imagine that doing that wasn't easy. This is another drawing that I don't understand any longer, of the connection between the footbridge and the support, because you have to guarantee too the expansion joints. Because the supports, as you see here, they are so short that if you don't let the footbridge to slide over the supports, the bending moment that you have here, they are enormous. So you have to create this sliding joint to free those movements. And this I'm going to skip, because Jorge is going to kill me. Thank you very much.
Thank you very much. I think we have some time for questions. Questions from the floor here. Yes, David.
I have one question for Professor Miguel Fernández. about textile reinforcement. You mentioned that carbon fibers are used, which are brittle. Have you maybe tried using other types of fibers? And can you say maybe something about the use of these types of elements in practice? Are they prefabricated like high profiles, or are they applied in any other way?
What's the last question? Sorry.
The first and the last.
The last question.
The last one was how is it applied in practice? Are there some structures where this kind of concrete is used?
Okay. So in textile concrete, it is used carbon, glass, and also there are other more like aramid and so on. Glass, it's less used. First of all, because you have to put an additive just to prevent the reaction between the glass and the aggregates to occur. But in terms of what we are using by default is the carbon one. So this carbon, in any case, there are also different types, and the one which is being more used is normally one that has silica impregnation, so it is a fully coated. You get the carbon fibers, and then it is fully impregnated with epoxy, and on top of the epoxy you have a silica, small very dots, that create some roughness so to improve bond. And these are the ones that are used more and more. But all of them, they are very brittle. All of them, once you get to the tension, boom.
I asked because maybe if aramid is used, maybe you get a different response.
All the commercials that I've seen, they are extremely brittle. One interesting thing is if you combine fibers, because there are some fibers that are having different modulus of elasticity and different strengths as failure. So you can combine more rigid fibers with more, let's say, less rigid fabrics. And this is creating a gradual failure. And this is introducing toughness. Another way of introducing toughness in the material is the use of fibers, but of metallic fibers, or let's say conventional fibers. Yes. And this is also introduced. There has been works now in the Polytechnique de Milano, for instance, on that. And that's a way of dissipating energy in the cracks. Textile concrete creates lots of cracks. And then with the fibers, we are dissipating, we're introducing toughness, a bit more toughness. Well, these are lines that are still open, I would say. In terms also, how is it used? I would say the country which is more developed in terms of use is Germany. Germany, they have facade panels, and they are, and the widest application of textile concrete nowadays is strengthening. So, for instance, I have used it, but many engineers, when you are, for instance, strengthening columns, it's just wrapping this textile and projecting concrete, this mortar, so that you confine the concrete. And this is, I would say, top one application that I can ensure, but there has been many interesting developments. There is also a footbridge that has been built, but they are more experimental character. I would say that it is the lack of a structural code which is giving you precisely what the values of the partial safety factors are, or methods of design, which is lacking to encourage this technology to go.
Also, I see the elements are much slimmer, so probably there is a instability.
Exactly. It is, as you saw in the pictures, it is in terms of mechanical response, is more close even to steel construction, as also the shell that I was showing 10 centimeters here, it is 9 millimeters, so buckling of the shells, it is governing. Yeah. And also other topic which is governing, and we don't know how to solve it yet, but this is to be done in conjunction with architecture, is the way you introduce, for instance, thermal insulation, acoustic insulation, because it's very nice when we see we are only consuming 9 millimeters of material, but the issue is that when you are walking, you are hearing it, or when you are speaking, you are hearing in the other side. So we still need mass to create insulation, and this is still not solved. This requires still
one more thing just related to this, because all the elements are very thin. Also, the example, the structure, shell structure to show. also very thin. Are there any issues with maintenance or margin of error when constructing probably is also much lower?
Yes.
1 centimeter is missing from 10 centimeters, it's
Yes.
10%.
In terms of maintenance, it is working very nice. This pavilion that I showed, for instance, we started building it because we build it each year it was 2017 or 2011 that we made the first modules, and we are following it every year, and it's behaving very nice. So I think there's no corrosion. It's very, very, very nice. So I think this is completely solved. And you were pointing also, sorry, the second part of the question?
Related to textile reinforcement.
Yes.
I asked if it is maybe used in prefabricated elements.
Yes.
Maybe in high profile or something.
Yes. Well, you said something interesting, sorry, on the sensitivity. Yeah, on the sensitivity. And when we did the shell, or the 10 centimeter shell, the formwork was so stiff because when you are having deviations in the construction tolerances that are in the order of magnitude of the thickness, then the buckling load, you see it clearly, it drops radically. So you cannot deviate much because you can use, for instance, a pneumatic formworks. No? You put like a pneumatic membrane, you inflate it, and then you do a projection. Yeah? But a pneumatic formwork, it deforms a lot when you are doing projection. So the shape that you are having, it is getting exactly some centimeters, but when you have 10 centimeters thick and your imperfection is of some centimeters, then your buckling load diminishes. And this is a penalty that you have when obviously it turns to be 9 millimeters, because if you are deviating from millimeters, then let's say you could have an issue. So this will require that you do a work, let's say, also on the formworks and on the stiffness of the formworks or active formworks that may correct defects. No? This is
because for even much simpler structures, the error up to 1 centimeter is
Yeah. Well, it's also 1 centimeter depending also on the length that it is done, the construction tolerance. But this is an open issue that, well, also of course steel structures might be sensitive to. So it's something that I would say it still requires some work. But basically, if we want to push this technology, which I think is very promising further, I think what we need is to have also structural design guidelines, not only to show that on average it works well, but when you are going to do a project on that, you need to have the design value. No? So this is missing. This is still missing.
Otherwise, you have to make research.
Yeah.
Thank you. That's good space for the anyone with a question? First of all, I need to be politically correct. You saw that the colleague left already. This is not a steel structures department. I would say that it's a polymer department. Okay. To be neutral at the moment. Okay. One question for you relates to those connections that you've shown, really complex, but okay, they happen and we have to design, build and calculate. So what is your views on using design softwares that can give you in a black box solutions for these types of things that, as you say,
when we did this was in 2009. So Idea Statica didn't exist at that moment, for example, for talking about what kind of software that is broadly used now. So we did it, I think, I don't remember exactly, but I have the feeling that we did it in a certain way by hand, in the sense that we say where the force is coming from and where it has to go to, and which are the path of loads and how can it be built. So the idea is we thought carefully at every bar that was coming to this connection, which were the forces that could be skipped in the connection. We decided to give priority to the longitudinal bars, of course, and they were through, and then we said, we analyze at each of the diagonals which of the 4 plates of each diagonal could be released, taking into account that maybe the bending moment there at that connection was smaller, but wasn't full capacity. And then we decided to release, in certain cases, some plates. And for the remaining plates, we placed just the path as direct as possible to guarantee that the forces could go through. But there wasn't, I think, we could have never used a conventional program, because that joint is not included in any conventional program. So what we need was to understand what we had to do with the structure to guarantee the global behavior. I don't know if this satisfying answer.
Maybe this is just a provocative question, just to continue over dinner for Miguel Ruiz. You showed your life cycle calculations. And my statement is, if I brought someone from timber or someone from steel, I would have different conclusions.
Yes.
But we have support from the standards. So how do you...
Very pertinent question. So we have the same one. So we went to the Swiss timber lobby, which is called Lignum, and we said, we are a bit surprised because this is what we are getting. Could you advise on that? And they engaged an expert on that, 300 euros per hour. And we say, do you want to pay the invoice? We say, well, you know, we are in research and so on. And they paid for that. And it came the expert and said, yes, you got the right answer. Yes, it's that way. And we said, okay, so the calculations were fine. But the people from the timber lobby, they were not, I would say, they were not against that. Actually, they were looking, that was very intelligent, they were looking for the opportunities. They said, where are we putting the CO2? And we and also the expert they engaged, saying, well, in the metal pieces that are, because they are galvanized, and these are very consuming in terms of CO2. And then they say, okay, we could perhaps develop some connection techniques based on timber and so on. So they saw that also as an interesting exercise for them, a valuable exercise for them. So we kept very good, and we were not saying timber is worse than concrete. I only think that we have to simply to claim that a good concrete structure, efficient concrete structure with efficient material selection for the concrete can be as good or as bad as a timber structure. This is all we can learn. But that the values they are correct, I think everything is a bit debatable because the sources where they come, of course, they have some ranges, but they are not that, they shall not be that far from what others may obtain. So at least we did the check.
I think that perhaps you should also get from the steel side an expert. We have some at 300 euros.
Okay, very glad.
Corroborate.
Yes. No, for the steel construction, we didn't go to an expert, but I think we got no. But it's a good comment in any case. What I can say is that if you are using recycled steel, which is in Europe at least is what we are using, it is as good as bad as the others. The issue comes when you are using non-recycled steel. This is where it simply explodes. But well, the message is go to recycled steel, no? But if you do an efficient structure, it is as good or as bad as the others. Yeah.
Thank you very much. I would like to thank Miguel Ruiz and Miguel Navarro for these excellent presentations.
Okay, thank you. Thank you for your presence.
And for the audience, this is the last session in this